Well, good afternoon. Mrs. D asked me to come and talk to you a little bit about some of the research going on in my lab. I actually just recently moved from Penn, and I'm now half-time at Cornell in New York City and half-time for Samsung Research. So the fundamental objective of what I'm studying is really to think about, when we try to build, say, artificially intelligent systems, and we want to compare them to kind of what we know about human or animal intelligence, how much do we need to do to slavishly copy biology? How much can we come up on our own in terms of the AI systems? And kind of what is going to be needed to be able to really build, say, future intelligent systems? So when we compare kind of machines to biology, I think one interesting thing to do is to do these kind of man versus machine contests. There's a long history of this. IBM, back in '97, built a Deep Blue that beat the world's best Kasparov, the world's best human chess player. More recently, Jeopardy was solved as a kind of, again, with IBM. And then just a couple years ago, Google DeepMind beat the world's best Go players. So these are kind of all indications that somehow that artificial intelligence was almost exceeding human capacities in these types of tasks. So the question is kind of what's the future? And if you watch Hollywood, right, if you watch the movies, there's a long history of kind of AI, robots in the movies where we see kind of them having these incredible superhuman capabilities. And it's always interesting because you know kind of what generation you're in, depending upon which robots you've seen. So has anyone actually seen all of these movies? Yes? Okay, good. We got some science fiction buffs here. So, but yeah, all the way from the 50s all the way to today. So the question is kind of when you build intelligent systems, I mean, what's the kind of way of breaking it down and trying to build the different components of the system, and how do you get it to all work together? So the way we do it in robotics is we take and we break up the whole, what we call perception action cycle. We think about kind of what we're taking in information from the world through our sensors. How do we build representations of that external world? Once we make a model of the world, then how do we do some sort of planning or decision making? And then once we make some decisions, we have to basically map out kind of where we're going to go in the world and actuate things. So that's the control side. So what we do is each of these areas, in order to make a system work, you'd actually have to make all of these things work carefully. So as an example, right, you can think about trying to build, say, an autonomous driving system, a self-driving car. Right? This is the car that my students put together 10 years ago for the DARPA Urban Challenge. And the way you engineer this system is you think about that kind of perception, decision-making, mapping, navigation, control, and you put together all these little modules that are doing things like taking your sensor information, making world estimates, figuring out where the objects are, making some sort of maps. Then you have some sort of higher level state machines that are trying to decide where to go. Then you try to generate trajectories to follow. Then you feed that down into your local motor controllers to actually actuate your robot. So if you do this properly, this is what you get. This is our work at the DARPA Urban Challenge. So, right, you have a car. So it's following. It's completely self-driving. It's sensing this vehicle in front of it. It's mapping that out. It's then sensing and this is an intersection, so it's a four-way stop. You then have to know when the vehicle goes through the intersection. And in this case, there's a stop sign. It then stops. It then senses that this car is in the roadway first, right? So it's waiting for this car to go through the intersection. And then at this point, this robot actually has a software bug in it, so it's not moving. So then the rules then said after 45 seconds, you can actually go out of turn. So then the system is waiting for that 45 seconds, mapping out a right-hand turn. It then makes this turn. And after it makes this turn, what's happened is there's another robot that actually tried to illegally pass this stuck robot. So what happens then is as we make this turn, we go past the stuck robot, and we come face to face with another robot car that's going the wrong direction in the lane. So then there's a couple human drivers during this competition that said, look, these robots are going crazy. They don't know what to do. This human driver backs up. Then the mapping sees enough area here to make a pass maneuver, go around the stuck vehicle, and then continue driving the rest of the course. So that's the kind of thing that you can do, right, if you actually think carefully about engineering all this perception, mapping, control together to make this kind of system. Now, what's happened recently is instead of having a human trying to figure out all these different modules, the idea is, can we actually just learn that from basically taking data from all the human drivers that are driving out there, put that all together, and just map kind of end to end, figure out what we can do with our sensors, putting that through, say, some sort of neural network, and then coming up with actually the control actions directly, right? That's kind of now what all the big companies in this area are trying to do, this type of machine learned way of controlling a robot. Now, what makes this hard, right, when you do machine learning? What makes this hard is the invariance problem. Now, the way we think about invariances is you have some sensor input, say a camera, or if you're in biology, you think about your retinal inputs. You think about all the pixels coming in. You can think about a snapshot of the world as a big high-dimensional vector. Now, what happens is when you're trying to recognize an object, say a dog, what happens is that this dog could be rotated slightly physically, or it could be kind of closer to you or farther away from you, and you have to be able to recognize that that's still the same dog even though it's going through these physical transformations. Now, what happens geometrically then is each of these instances of this dog is a high-dimensional feature vector, and then what happens is as you kind of rotate and scale the dog, it becomes what we call a manifold in this high-dimensional feature space. And so what you actually have to do is figure out how to represent these different manifolds, so that a manifold of a dog versus a manifold of a cat, to be able to distinguish these two different objects from each other. Okay? So kind of mathematically what we can then do is think about the geometry of these manifolds in these high-dimensional spaces and try to characterize kind of what makes certain manifolds distinguishable from other manifolds using very simple types of classification systems. Right? And so if you get, I don't have time to get into details, but this then relates to convex geometries of shapes in high-dimensional spaces, and you can then do the statistics of this to try to figure out how to analyze these kind of machine learned systems when they're successful and when they're not successful. And so this is then the excitement is now taking these types of systems and analyzing what's called a deep neural network, trying to figure out how the different representations change as you go through the different layers of this network, and how that relates to how our representations in our brain change when you go from, say, the retinal level to V1 to V2 to V4 to inferior temporal cortex when we do recognition in our brain. Okay? So if you do all this carefully, you can start to now think about doing other kinds of fun things. So one thing that our students worked on is taking perception, taking the planner, doing control, and playing soccer with them. So this is actually an autonomous soccer team, robot soccer team. Our robots are the small robots. They're seeing the ball, they're tracking the ball, they're fighting over it, right? They're bumping into each other. It's very difficult to do the locomotion and the balancing. And now you see kind of our robots tracking this ball. He's now going to take a shot against the goalie. The goalie sees the ball coming, makes a diving save, right? And then when the goalie gets up, the problem is that the goalie can't see where the ball is anymore, right? Like sometimes a bad goalie does. And so it gives enough time for our forward to come in and shoot the ball into the net, right? So that's kind of what you can do if you get this right. But a lot of times in robotics, you get it wrong. So real robots it's very difficult to get them to work very well. This was actually from a recent robotics challenge. You see how difficult it is even to stand up. So these are all the top US teams for DARPA. This is Carnegie Mellon's robot falling through the doorway. This was, again, a robot from Boston Dynamics falling on top of the rubble pile, just being able to stand on the side. And so you see kind of complete systems failures. Right, this is just not even getting the first step. Right, this is interesting. It's trying to turn the door handle and it falls off the door. This is trying to climb the stairs, falling backwards off the stairs. We also, I think, this is trying to walk sideways through the door, but falling on its side. This is another one trying to get to this valve to turn the valve, but falling over. I think this is interesting. This is a Japanese robot. It's trying to grab a wheel, this valve. It's turning it, but it's not turning anything. So it basically torques itself over. And this is just now a complete system. This is our team, actually. And so we actually fell and had the indignity of having the drill fall on us. This is MIT's team coming off the Jeep. And it has some sort of Parkinsonian disease because you see it kind of struggling here and then doing a face plant. So this is still, an active area because we haven't solved any of these problems. And compared to biology, as we saw with the jumping spiders, biology is amazing. So this is actually a 12-year-old, the US champion in cup stacking. Right? You see that he's tracking the different cups. He's able to control his different hands. He's doing haptic feedback, and he's basically able to do the stacking and unstacking. This is orders of magnitude better than what we can do with our machines right now. So this is really the I think vision is that can some of these mathematical techniques, some of these ways of thinking of putting this problem together, can we then make progress in actually building real intelligent systems that will actually interact with the physical world and be able to do it as well as what we know what animals and humans are able to do. So that's it. I just wanted to thank all the students that are working on these projects. Happy to take any questions. Yep, question?
What's your best hope for a breakthrough?
I mean, there's a lot of problems, right? So there's the sensing side of things, being able to do recognition, being able to do fast planning, being able to do kind of good feedback control, again, building better actuators, building better batteries. I mean, these are all the things that make this problem difficult. But we're slowly making progress at each stage. Now, I think it's not going to be as fast as some people think, right? Some people think that super intelligence and killer robots are kind of around the corner. That's definitely not true, but we are making steady progress with a lot of kind of interesting ideas, scientific ideas in the mix. So
you don't think there's one dimension that's just going to blow out progress in cup stacking or these near-term perceptual kinetic tasks?
I think you have to have different ideas put together because we do a very complicated interplay of the haptics, the vision, the planning. I mean, so in order, I think, to build a system that's comparable, we'd also have to make progress on all those fronts. Yep, question?
Kind of a follow-up to that, what do you see as the role of reinforcement learning going forward?
Yeah, so reinforcement learning is interesting. We are using some of that in our systems. The idea is typical machine learned systems are using what's called supervised learning, where you have kind of humans labeling the output, like for this input, do this output. For this input, do this output. For this input, do this output. Reinforcement learning is more like when you train your dog. The dog does a lot of things, and every now and then does something nice, so you give it a biscuit, right? That's kind of a good reward. Or if it does something bad, you'll be like, bad dog, right? So it doesn't give kind of an input-output labeling for every time. It kind of gives just sparse set of good or bad rewards. And the question is, can we get systems to learn from that kind of more sparse set of rewards? Even more critical is, can we do unsupervised learning, which is that you don't have a teacher. It's almost like you're just exploring the world on your own. You're trying to figure it out. You're trying to figure out what to do without someone explicitly teaching you, like, do this, do that, do this, do this. You're actually doing it on your own. And that's even a more challenging problem. And those are the things that animals and humans do very well, right? We don't have a teacher explicitly telling us every second of the day what to do. We're able to figure out the world on our own, statistically and from these kinds of models. And so how can we put that into these robots? Okay. Question?
In your sort of title slide, you mentioned, of course, your university base and also that you work with Samsung. So relatively speaking, do you see companies or universities as the cutting edge of this field?
Yeah, so it's an interesting question because I think in AI and robotics these days, you see a lot more funding coming from the industry right now. So, Google, Facebook, Toyota, Samsung, everyone is trying to build these systems because they see that as the future for their companies. And so for faculty and students, there's actually a lot more resources available funding-wise from the companies. The US government is trying to catch up, but they just cannot compete in terms of the amount of resources that the companies are putting in right now. So that's, I think, for a lot of faculty like myself, that's why and we feel that the academic side is super important because we want to educate the next generation of researchers, but we would like to be able to utilize the resources that the funding agencies don't currently provide in the government. And this is why, having kind of dual appointments is very attractive.
So the performance is still universal. I was thinking of the example yesterday when it was pointed out or was it this morning, that DuPont's monopoly position allowed for a lot of basic research, and that's out. So I just wondering how these things relate. The companies that you mentioned that are putting in a lot of funding are in very competitive fields and fighting hard and worried about quarterly results.
Yeah, no, before I went to university, I was at Bell Labs for a number of years. And Bell Labs was, again, a place where it was, at that time, just ending the monopoly. But it was a great place to be because they had all the resources and they had the intellectual freedom to pursue those goals. And that's what spurred a lot of the developments that I think we're still cashing in on today, right? The transistor, the CCDs, all those things. And so what we would like to be able to do is think about for the future, where is this kind of innovation going to come from? Where can we fund the best and brightest people to come together and really work together in good teams to build the next wave of technologies? That's important. Question?
Actually, a question about applications. If we get to the cup-stacking stage, all sorts of stuff, right? But what are some intermediate stages you see in terms of applications that we're not there yet, but can get there before we get to the sort of biological equivalents?
Well, so like for instance, autonomous driving. I mean, if you're going to do it in a more structured environment, say on the highways, that's typically, I think technologically is almost there. Right, that if you have control of the barrier, you don't have people walking around, you don't have cyclists walking around on your highways, you could do that. Maybe delivery systems, if you had controlled environment, the more controlled of an environment is, the better it is, and you can actually make an application out of it right now. But the less controlled, right, that you have people wandering in, all these kinds of dangerous situations, then we still can't handle that. So I think you'll see a titration of kind of what we can do in terms of applications, what companies can do, and then they'll start to expand as the technology gets better. All right, thank you very much.